suppose you have an integral of some function that is dependent on another function y of x, as well as its derivative y prime of x. And the question is, how do I minimize this integral? What function y of x will minimize this integral? Well, the idea is that we want to turn this I into a function of epsilon, some other variable. Well, I'll say I bar of epsilon, such that if we were to take the derivative of it with respect to epsilon and set that equal to 0, we'll be able to solve for the function y. So basically what I'm saying is I'll assume that y is the solution. Okay, so I'll say y is the solution, but I'll add some variation epsilon times another function, eta of x, and I'll call that y bar of x, that kind of variation. And that'll also give me a derivative of y bar, and that'll just be the derivative of y plus epsilon eta prime of x, right? Because epsilon is still an independent variable relative to x, so that won't do anything. So now I'll have this I bar of epsilon, which is equal to the integral from a to b of f of y bar comma y bar prime dx. And the idea is that I'm just going to be taking the derivative of this function with respect to epsilon at epsilon is equal to 0 and setting that equal to 0. Because if we imagine I bar of epsilon, if we imagine it as a function, this will give me a minimal value or a maximal value, right? It could also be look like this. When epsilon is equal to 0, this will either give me a maximum value or a minimal value. So that's the idea. So I want to take the derivative of I bar with respect to epsilon, and I'll get 0 from it. So let's do that. So if I actually do this, I'll be able to bring the derivative inside of the integral, because again, epsilon is independent of x. So I'll just do this in there. So the way I'll do it is by taking the derivative of f with respect to y bar, and then the derivative of y bar with respect to epsilon. And then to that I'll add the other derivative, partial f partial y bar prime, partial y bar prime, partial epsilon, and then my dx. Now if we just look over here, we can read off what that derivative will be. So this will just be eta, and this will be eta prime. Okay? And if we do a bit of integration by parts, we'll get that we can rewrite this expression as the integral from a to b, partial f partial y bar minus d dx partial f partial y bar prime times eta dx, and then I'll have some extra term that's going to be partial f partial y bar prime times eta evaluated from a to b. But we know that eta is supposed to be, so if I draw a graph of eta from a to b, this is what it'll look like. It'll be some kind of variation, but it will have to be 0 at a and b. So that means this will just be 0. And since we already stated that the derivative is supposed to be 0, that means if eta can be any function we want, as long as it's 0 at a and b, then that means this must be 0. And from there, we get the Euler-Lagrange equation. So, and also this is evaluated at epsilon is equal to 0. And when that's the case, y bar just reduces to y. So epsilon is 0, and we just get this back, right, for both of these. So this is 0, you just get this back. So in this case, we'll just get that partial f, partial y, partial minus d dx, partial f, partial y prime is equal to 0. And that's the Euler-Lagrange equation.